All right, thanks everybody for those of you that have stayed the whole day and are still here for my talk, my very data-centric talk. It'll maybe be a little bit of a departure from some of the other talks you went to today. But I'll start with a little bit of background that isn't covered by the other slides here. So yeah, I'm Patrick. I'm a principal engineer working for Amazon, specifically working for a division of Amazon that manages a centralized data lakehouse for Amazon's various business units. And increasingly what we've seen in recent years as more of the organizations that we serve internally in Amazon are getting involved with AI, and things like AI-driven fraud detection is becoming more popular, and we're seeing this transition from manually derived business intelligence insights to insights that are derived with like some degree of supervised machine learning, and then over to unsupervised insight derivation. It's becoming increasingly important to provide a low latency data processing pipeline that runs cheaply and as quickly as possible at exabyte scale for people to get critical insights about fraud in their businesses or other related insights as quickly as possible, and to use the best standardized tools that we can find in open source and closed and otherwise to meet these demands. So that's kind of the context around this talk and why we've started working on these problems and why we've started open sourcing some of the solutions to them in our Ray ecosystem project, which is called DeltaCAT, which we'll get into. So a quick overview of what we're going to cover here. First, I'm going to give you a brief history of business intelligence at Amazon and how we came to own this big exabyte scale data lake house for everybody. And then we'll talk a little bit about Apache Iceberg and the nascent Ray DeltaCAT project. And we'll talk about the iceberg streaming problem, or as it's sometimes been called, if you like Google, the iceberg equality delete problem. It's kind of another word for what I'll say is the same thing. And then we'll talk about an open exabyte scale solution that we have created for this, that we're contributing to open source as part of the Ray project under an Apache v2 license. And we'll quickly review the current state, some of the results we have, future work that we have planned. So starting off, I'll give you the history of Amazon Business Intelligence, at least as I know it. I joined Amazon in 2016. And in 2016, Amazon was in the midst of deprecating their petabyte scale Oracle data warehouse. Specifically, we were trying to migrate 50 petabytes of managed data from a whole slew of different Oracle clusters over to an S3-based data catalog. And that is about how vague the problem statement was at the time. You know, there wasn't any specification to be followed around how you were going to create this data catalog or keep anything working. Just like, you know, figure it out, guys. So that also resulted in the post that you see from our CTO, Werner Vogel's there on Twitter. When we completed the migration, he noted that the Oracle data warehouse we were maintaining was one of the largest, if not the largest in the world, and we've moved on to other things. And we gave a nod to Redshift there, which was one of the first key query technologies we relied on to query our data from S3 instead of Oracle. But our goal really wasn't just to query it with Redshift. It was to decouple storage and compute so that we could query our data with theoretically anything and produce it with theoretically anything. And so that leads us to 2018, 2019, where we got a little bit more organized about our approach. Right? In the early days of data lakes, they were often known by the pejorative of data swamp because they had no rules, there was no ACID compliance, and where there is no rules and there is no structure, you just basically have a big bucket full of files and nobody really knows what's going on. So the data lakehouse was a term first coined by Databricks, I believe. And that basically says, hey, you know, it doesn't have to be one way or the other. It doesn't have to be data lake or database, and one is ACID compliant and the other is not. You can actually follow some strict rules here and get your compute and storage layers to work together such that you can have ACID compliance together with your data lake, and we'll call it a data lakehouse instead of a data warehouse. One of the key problems we got into is this so-called compaction problem when making a data lakehouse specification. So basically, our data lake would allow people to record logs, and each of these logs inside of our data lake would say, hey, append these files, or update these files, or delete these files. So the simplest way that you can visualize compaction here is by just saying you're appending ordered files that contain a certain number of records. When you're doing this simple operation, you get a tiny file problem after a while, where if you guys have ever tried to download like thousands or millions of tiny files over the web, it's super slow, right? Just the latency of fetching them over and over again. So compaction, initially, in its simplest form, just says, hey, those records you appended, I'll just stitch them together into a larger singular file, or 256 to 1 gigabyte files each, if it's like Parquet, snappy compressed. And then you can read those larger files a bit more efficiently as a consumer. So we started doing that initially on Apache Spark, and we'd create these compacted snapshots of the tables. Basically, we're just creating a read-optimized version of the table. A slightly more complex variation of compaction now involves a deduplication problem. You specify a merge key, which is kind of like a primary key. Iceberg calls it like an identifier key ID. In this case, we say column 1 is that merge key. And so if we load 2 deltas, and the second delta is loaded after the first delta there, then we update the records with the later column 2 values from delta 2 that have a matching column 1 value, and we insert records that don't have a matching column 1 value. Pretty common to see this sort of upsert-based workflow working in like CDC type applications. So that's upsert-based compaction, right? We're still creating size normalized files. We're still getting rid of the tiny file problem, but now we have a hard, potentially petabyte or greater scale deduplication problem to wrestle with along the way. And it turned out a few years later, Spark was breaking the bank in terms of just how much it costs to do this in an exabyte-scale data lake. So we started looking for other solutions, and we stumbled upon Ray, and met with the team in 2019 at UC Berkeley Rise Lab that was working on it, and thought that the core primitives that Ray provided of tasks and actors could give us what we need to build a custom compactor that would be much more efficient at this problem. So in 2019 to 2023, we initially kicked the tires on Ray, did basic distributed systems tests with it to just prove its viability as a distributed system. We were also thinking it would serve as, if it passed these tests, it would serve as a very good tool for a lot of our machine learning engineers and our applied scientists and other folks to use that preferred Pythonic APIs, but also wanted these APIs to scale to the volume of data we managed. So we had kind of 2 objectives in mind here, but optimizing compaction was the first, and we started shadowing these compaction jobs that we were doing on Spark with Ray. So you can see we'd tie Ray and Spark into the Delta stream of updates coming into the table. We'd create equivalent compacted tables on each side. We'd have data reconciliation services and Ray-based data quality services comparing all of the results on each side to make sure that all data consumers saw the same thing and that all key statistics of the data set checked out. And we called this the shadow compaction workflow on Ray. Right now we're spending twice the money just to prove that we can eventually save money someday. That was a hard one to sell, but I think it was a very important engineering milestone. And yeah, the result there is pretty key. Like, we published an AWS open source blog post about this called Amazon's Exabyte-scale migration from Spark to Ray. We were able to prove that we can reduce the cost on average by about 82%, which is equivalent to about $120 million a year in EC2 on-demand charges for the workload sizes we were running at the time. So substantial savings by just making a purpose-built distributed application that ran this compaction operation on Ray. And there's just a historic graph kind of showing you that IM, or instance minutes per gigabyte metric was how we measured it. So equivalent instance minutes on equivalent, instance minutes on equivalent instance types to compact a gigabyte of data is how we typically measured efficiency and compared them between Spark and Ray or competing platforms here. And from 2023 until now, we've been working on gradually shifting into a position of Ray exclusivity, where Ray is just compacting and managing, creating the read-optimized version of all the tables in our catalog. And we've also contributed an open source implementation of our compactor to the DeltaCAT project. And looking beyond 2025, and something we've already started this year as well, we're working on lakehouse unification. Some other interesting projects here. I don't know if any of you have also maybe heard of Apache Xtable or Gravitino or these other projects, but Unity catalog from Databricks. There seems to be quite a few projects popping up in this area of lakehouse unification, and it's becoming increasingly important to us as well. One of the things we're noticing is maybe there's not really one table format to rule them all amongst Hoodie and Delta Lake and Iceberg for now and DeltaCAT that we're working on and using internally and gravitating towards for multimodal data management. Maybe you are going to need to try to extract the best of each of these formats. So we've thought it's important to be able to say, do something like, hey, write your Parquet files once, the expensive part of your data workload, and then the cheaper part of it, and this is much easier said than done, of course, take the metadata that you would put in Iceberg or Hoodie or Delta Lake or wherever, and just translate that and convert that across systems. So that's how we're kind of thinking about lakehouse unification right now. We're kind of experimenting and probing in that direction. And that brings us to maybe introducing DeltaCAT and how it fits into this picture really quick. Well, DeltaCAT is fundamentally a portable multimodal lakehouse. And similar to Ray, we try to follow the portable part of it means from laptop to cloud. You should be able to run it on your laptop and simulate the same results that you would get with a production cloud distributed workload. And it contains 4 key components: a catalog component, which is basically high-level management and discovery, APIs for DeltaCAT, a compute component, which manages these things like the compaction job to create read-optimized data sets, this interesting delete conversion job, which we'll get into shortly, some other statistics collection jobs, just key plumbing that keeps your lakehouse moving, and that most people, except for like lakehouse administrators, shouldn't really need to know about. And it has a storage layer for in-memory and on-disk multimodal dataset formats, and a synchronization layer, which is still in development, that we use to, again, synchronize that metadata between a DeltaCAT table format or a dataset format and, say, an Iceberg or Hoodie or Delta Lake format if they're compatible. Version 1. I think like 1.7 or something was the last one we were using in production at Amazon for compaction, and we've recently released version 2.0 out to open source that everyone else can start kicking the tires on and playing around with, because version 1 was kind of overfit to Amazon's use case and wasn't a great fit to just contribute right back to open source. It relied on too much internal plumbing at Amazon to actually make the thing start up and start working for you. And a quick overview of how DeltaCAT works now. So basically, if you start from the top left of this diagram, you have the data producer there, and he's going to write data to a managed data lake, effectively. And he's going to write maybe Parquet files, maybe Lance files, maybe he's going to write ORC or tensors or images or audio or video. We don't exactly care. We're kind of unopinionated about that, except for the fact that it should be something that we can put inside of one of the following dataset formats, which we support for I/O in DeltaCAT, which is Ray or Ray data, fundamentally, which is All these things are also built on top of PyArrow and have PyArrow cross-compatibility at their foundation, or Daft, or Pandas, or NumPy, or Polars are the main formats we support for loading data and reading data into DeltaCAT tables. And so the goal is, if you're just a Pythonic data consumer or data producer, you stay in that loop. But we know that there's also this world of Iceberg tables and Spark and Trino and Flink, so thus the synchronizer component to also say, well, we can also do an eventually consistent synchronization of the metadata. We won't copy the data files into Iceberg, Delta Lake, Hive, Hoodie, so that you can continue to use Spark and these other frameworks to query your data if you want to break out of that Python and Ray-only loop. So how does it work? I'll briefly cover this. Well, you can just start by running pip install DeltaCAT. And to write to a table, if you ignore the comments, it's really, in the imports, about 3 lines of code. We're importing DeltaCAT and Pandas first. In this case, we're calling init local to just initialize the local catalog, which will be .deltacat in your current working directory. And we create a pandas data frame and just call dc.write to write it to a table. The table will be created. It'll contain the pandas data frame. And then you can read from the table using a Daft data frame. That's our default, just by saying dc.read and providing the name of the table. The namespace in this case is implicit and defaulted as well. So these are meant to be very lightweight APIs. And you can also read its array data set, like we said, pandas data frame, PyArrow, or whatever you want, just by specifying the read as data set type that you'd like. And there's some other cool things you can do. Live feature enrichment is one of the things we focus on. It's kind of a side effect that came from working on the compaction problem. The DeltaCAT turns out to be very fast and scalable at adding an almost arbitrarily large number of new fields to your data, storing them in separate Parquet files, and then stitching them back together for you. Either at runtime or, again, the compactor can materialize these things together. And so updates to existing records with a merge key or adding new fields that are aligned by merge key are one of the things that came as a side effect. And making very fast live feature enrichment kind of came as a side effect of working on the compaction problem. And multi-table transactions is another thing you just do with DeltaCAT.transaction, and you can create, say, a user data and a corresponding finance data table for your users and make sure that either they're both created together or neither, so you don't have, accounting discrepancies. So those are a few of the key features here. There's many more. We have examples on the front page now. We didn't for a very long time. So schemaless tables we found to be important for managing multimodal data, ordered and unordered writes, multi-table time travel, batch inference, and cross-catalog management and sharing are beyond the scope of this talk. And now let's talk about Iceberg very quickly. For those of you that don't know about Iceberg, basically Iceberg has a core root table metadata file. Iceberg is a table format. It knows about a table. It needs an external catalog manager like Glue or something to know about all the tables in a catalog. So fundamentally, Iceberg starts with a root table metadata file. Your table is composed of snapshots. It's basically like, this is what the table looks like, and these are the files it's composed of at this point in time. And it has Java and Python interfaces for like a nice REST catalog implementation that Iceberg provides that lets you actually interact with all the tables in a catalog, organize them by namespaces, explore and manage, again, all of the tables that are described by this table metadata format. If you look inside an Iceberg data directory, you'll see these kind of Hive partition-styled directories at first, where you have this like equals sign to delimit what your field is on the left and your partition value on the right. And if you dig into one of those partition directories, you can see the actual like Parquet data file sitting in there for that partition. And inside of an Iceberg table directory, it has the data directory and a metadata directory. If you open up the metadata directory, you can see those components of an Iceberg table we talked about before. It uses Avro and JSON to describe those pieces of metadata that we were just talking about. So now let's get into the interesting part. So Iceberg equality deletes now are one of the things that Iceberg supports. And an Iceberg equality delete just says, hey, I gave you a predicate. Basically, these are the keys you need to find as a reader in the data set that these equality deletes are written to, and then you need to delete them at read time. So again, a large-scale deduplication problem. So Iceberg also has positional deletes. Let's share that work with the writer. So the writer now has to find the matching record indices and what file they belong to. So now it's cheaper. The reader doesn't have to find where all the matches exist. The writer already did that. So the reader just skips the record indices identified and the files identified. But you can do better in practice. Iceberg v3 specification introduces binary delete vectors, which are now just a binary representation of the same. We'll just write binary ones here to represent the first two records, which we deleted, and zeros for records that are kept. And those will live alongside these files to represent deleted records and kept records, just to make that reader process a little bit faster and more predictable. And that brings us to Iceberg copy on write, often abbreviated as COW. So I have some friendly cows there, so you know who's doing copy on write in this process. And a copy on write data producer, well, copy on write data production is very expensive. That's why he's a rich cow. So he has to find all of the duplicates inside of this maybe, who knows, terabyte, petabyte scale data set, and also has to materialize the new, say, Parquet file with all of those records that were found deleted. And then the data consumer can very cheaply read. So that's most expensive for data production, cheapest for data consumption. And then merge on read now splits the cost. The data producer has to pay a bit more to find where the matches are. Okay, I found your matches by merge key, and I identified which records you should ignore as a reader. The reader still has to pay a little bit to, get a bit of extra data and now ignore the data that wasn't physically deleted. And then Spark you can periodically run a rewrite data files job to update them and materialize them. So now you've amortized the cost of materializing all your files. You do it occasionally instead of after every job run, as in the cow model. So that's merge on read or more. And now that brings us to the problem we've had with this. So for merge on read tables, streaming frameworks like Flink prefer to write equality deletes because they're fast and conflict free. But there's a catch. If you write a lot of them to a large table, you might get out of memory errors on read. And people do in practice. And we did in practice. And then batch frameworks like Spark can only write, not prefer to write, positional deletes in Iceberg v2 or binary delete vectors in Iceberg v3. Now, that's cool, it's a balance again, but again, there is a problem here. They're higher latency, and you might get near resolvable write conflict because you ran like a concurrent compaction job, and now a positional delete raced with it, and you potentially have positional deletes pointing to files that no longer exist. They've been compacted and merged away, and now you've got to retry it and hope you don't get stuck in an infinite retry loop. And if you're talking about high-frequency writes, the odds are good that you'll get stuck in an infinite retry loop. So I say it's less practical for high-frequency writes at terabyte to petabyte scale. Copy on write tables are even more impractical because, again, they always rewrite the data files with the deletes applied. So now you're, in practice, kind of like doubling the latency of just finding the deletes. And this has been an issue for a while. So we have a series of PRs and issues that were raised and abandoned since 2020. We pulled up here. It's been a hard and messy problem to try to fix, in short. It's not that nobody wanted, people wanted to fix it. It was just difficult, and there always wound up being blockers to getting it done. So the position you're left in is basically this. You have a happy merge on read data producer on Flink side just pounding a table with equality deletes. But then you have a merge on read data consumer who maybe OOMs every time he tries to read it. And now you have a Spark rewrite data files action that also can't dig you out of this mess because it also OOMs every time it tries to read it. And you've now got basically a dead table. So after bumping into this problem, we said, oh, how about that? There's no actual solution we can find to it. So we wrote a new job type into DeltaCAT that says, hey, if Flink comes in and pounds the table with equality deletes, we'll take like that first half of the compactor we wrote and specialize it even more for just this problem. And we'll convert those equality deletes over to positional deletes, which is what Spark loves. And then we can all be happy. And we can have this tiered process of gradually more expensive reads. So we can basically convert equality deletes periodically. People who have a lot of money can read directly from the equality delete table, and if there's not a lot of equality deletes, they can probably survive. But once we convert the equality deletes, we know everybody can survive. And once we rewrite the updated data files, we know it's also totally optimized and cheap to read, so you can kind of amortize steps 2 and 3. Step 3 more than step 2, we've found. And another cool thing we've done, if any of you use Apache Beam today lets you just append data to an Iceberg table. That's it, simple enough. But we also found we could use this job to say, hey, well, if you're appending data to a table with Apache Beam and maybe running Flink or Google Dataflow with Beam, you could also tell DeltaCAT what you want your merge keys to be for that table and run it asynchronously, and it'll just create the equivalent positional or vector deletes for you. And again, let you go into this world where you're now doing upserts with Beam. And you can, again, use a Spark job to rewrite and compact your data files and normalize their sizes. And so, yeah, the results, we're still pretty early in the testing process. These are pretty much hot off the press as of last month. But so far, with the tables that we've onboarded, these are all production tables, and some of them include some of our largest tables, petabyte-scale in our catalog, where we've achieved an average execution time, managing these terabyte to petabyte scales, of about 27 seconds, which if we split hairs, we might say, like, well, it should be like sub-second for streaming. But at this scale, it was way better than we were at before, which is like 30 minutes and then an OOM. So 27 seconds felt pretty good here. The maximum cluster size we support for just stability reasons we've observed with Ray is usually about 4,000 vCPUs or about 125 R7G 8X large instances, which gives us a pretty good max throughput of about 907 terabytes per hour. And the efficiency is also looking very good here. I put just to kind of ground these figures a little bit, the 100 terabyte cloud sort cost record, which is also held by Ray, is about 97 cents per terabyte. And for us to do the delete conversion, we're sitting at about 55 cents per terabyte on demand, or 21 cents per terabyte if you use spot R7G instances on average. So we're pretty happy with how cheap and fast it is to dig ourselves out of this hole and no longer have dead Iceberg tables. And future work, if any of you all are interested, there's some GitHub issues to +1 related to, well, we haven't actually made like a full-sale, nice, easy-to-use integration with Flink, with a nice Flink IO connector yet. We haven't made a Python native Beam IO connector yet. It's kind of like stuck together in a ugly sort of way right now. And an older issue is we haven't written an array job that can do that positional or vector delete materialization for Iceberg yet. Spark's still the only one that I'm aware of that has an open source job that'll do that for you. So probably less opportunity to get cool cost and efficiency gains there, but it would be great if we could just run the full stack end-to-end on Ray, I think, and not have to run 2 competing frameworks where one of them is just rewriting your S3 files. So if you're interested, please +1 the issues. And thank you for your time. You can find me on Ray Slack almost anytime by my name. There's the link to the DeltaCAT project under the Ray project on GitHub and my GitHub profile. So yeah, thanks guys.
It's up. Hey, thank you. Very nice talk. So wondering, You showed the performance improvement after switching to Ray. How was the data look like when you were using Spark?
So for this one, right, we had a bit of a problem. When some of our largest tables, like say 10 terabyte plus tables, when we would load them at their usual cadence with Flink, since we already had Flink pipelines set up, like we have clickstream tables that are just being fed by Flink day in, day out, we were unable to complete most of our Spark jobs. So usually it was around 15 minutes, 30 minutes, and the job would fail. We'd get out-of-memory errors. So we don't have good baseline comparisons for Spark in that sense. Something that we still need to do and collect performance figures for is what is the performance of just writing the positional deletes in the first place on Spark versus doing this two-step write equality deletes with Flink, now convert them, right? So what's the time and cost trade-offs? I think we might still come out ahead, but it'd be pretty amazing if we did, because we're also reading from S3, which is adding latency.
Sorry, for one more follow-up question. Have you dealt with tables with tens of petabytes with this new compaction way?
In aggregate, yes, but we divide the job into partitions. So in an individual partition, so far we've dealt with about 100 terabytes at once.
And this is only for compaction. Have you dealt with upsert, or it's only append only?
Or yeah, sorry, it's these are upserts. So
All
yeah,
right.
we're doing equality delete conversion with merge keys. So fundamentally, upsert is the usual operation we're doing. Yeah.
And Patrick, can I request you to answer from the microphone?
Oh, good idea.
I have a question. Over here on your right.
All right, gotcha.
If you can see me.
Yeah.
Yeah. All right. Really interesting project. Just a quick question on the REST catalogs for Iceberg and so on and so forth. How do you see that pan out over the period of time? Maybe 6 months, a year down the line? Are you kind of thinking about having full portability across the board?
Yeah, data portability between these different table formats.
Yeah.
How do I see that playing out? I mean, I would love to see full portability. And with Iceberg kind of being in the Databricks fold now, I think you'll probably see increasing portability between Delta Lake and Iceberg. And Apache Xtable is a project that I think was started by some former Hoodie folks, and we've been using it internally as well to do some of these conversions. And it seems to work pretty well for allowing you to do, take advantage of the best of both worlds, do fast, high-frequency writes with Hoodie, and then do a metadata conversion and convert to Iceberg. So I would almost say, in a weird way, the pieces are already there. It's just not assembled into a nice user experience. There is much assembly required. And for me, the question is, well, you'll be able to do these things. You'll be able to convert between table formats, but how painful will it be? And will the main PMC members of these projects or the companies supporting them invest money in managed offerings to make it easier? I hope they do, but that one's kind of 50-50 for me. Right now. We're trying to do our best in making open source tools that also help and are hopefully easy to use eventually.
That's great. Good to know. Thank
Yeah.
you.
All right, any more questions? No. Thank you, Patrick.
All right. Thanks, everybody.